No, would you like to write some? Yes? Okay. Okay, so it's a pleasure to have here Filippo Radicchi, because I mean we have been working together the last I think 4 years probably. So it's a nice collaboration. And Filippo did the PhD in Bremen, in Germany, even though he did the master in Roma. He's from Rome. It's original. Then after the PhD, he did the first postdoc in Torino, in the SI Foundation where I was working. And after that, he moved to the summer group in Evanston. And after 1 year more, he went to Tarragona as a harmonica hub, where he just started. So, well, I mean, it's...
Thank you very much. Thank you to all of you for being here. I realized, I mean, today we talk about nice work. I mean, that I already started when I was in Torino, finished when I was in Evanston, and really published in January, but was already in Torino. Despite the title could be, it's a bit misleading, numbers. I will not talk about statistics about hunting, so killing animals. I mean, it's just really hunting, but numbers, like numbers 1, 2, 3, and so on. Nevertheless, I mean, the starting point is about animals. As probably you know, I mean, there are, of course, today with modern technology we can track more or less everything. And these studies about tracking started in the case of animals. So you can plug, basically, put a GPS device on a bird, and you can track the position in time of these animals in the environment. There were a lot of studies published only on very big journals like Nature Science and so on, covering a wide range of species, so birds, mammals, fishes, or even insects. And they were studying how animals move in the environment, looking basically for food. I mean, this is the main motivation because animals move in space. The nice thing is that there is a coherent picture about the statistical properties of these movement patterns of animals in nature. Basically, if you just take two positions, distance between two consecutive positions occupied by an animal in the space, and you just do a distribution of these quantities, they follow a power law. Of course, there are some limitations, both given by the, on one side you have the limitation of the resolution of the instrument that you are using for tracking the animal. On the other side, of course, you have the limitation, physical limitation, because, of course, animals cannot travel for very, very long distances. But nevertheless, on this, two order of magnitude, you can measure quite good power law distribution. Of course, this is what is called Levy flight, and is observed also in chemical and physical systems in different kind of contexts. But in general, the typical pattern that you can observe, like in a two-dimensional space, like you have like a pseudo random, standard random walk movement on this region, and from time to time you jump in another region and you start again to move locally. The main point is that apart of this coherent picture is the fact that the exponent of the power law that you measure is close to 2. And there was a nice study published by the group of study in 1999 in which they proved that this exponent, the value mu equal to 2, is optimal for searching scarce resources in the space. Basically, they model in a very simple way. They have a random walker performing Levy flight, with different variables. You can tune, of course, the exponent of the power distribution. Then you can just calculate the efficiency, so the number of targets that you hit divided by the distance that you cover on average. And in this case, as you can see, independently of the dimension, here is 1D lattice, I mean here you have 2D, you have a clear peak around mu equal to 2. Stating that, basically, if you look in a space with scarce resources, in this case, like in the case of animals, the resources are full, is full, and you do this randomly, the best thing that you can do is to move with a Levy flight with an exponent equal to 2. Now, this is what is valid for animals. But the point is that, I mean, also, what about humans then? Because, of course, you can explain such kind of things that you said in the case of animals with some speculation related to the evolution. You know, I mean, only the fittest survive and reproduce. Of course, you observe at the end that animals follow this optimal strategy when they look for something. But, of course, I mean, also in the case of people, I mean, if you look to just the evolution, I mean, we have a very, very long time in which we were just hunters, we were looking for food, moving in space, looking for resources. And only very recently, compared to the old evolution of the humans, of course, we started to, I mean, to farm, to grow our stuff. And we didn't longer need to move in the space in order to search for food. Regarding that, I mean, there are two recent studies about patterns of movements of humans in the space. One is a work published by Brockman in 2006, Brockman and collaborators, of course, we measured in 2006. And they were tracking indirectly people. Indirectly because basically they were using data coming from a website that was called, Where's George? So on this website they were distributing money, so banknotes, like a $1 bill, and with a stamp like with the name of this website. And people that ordered this money were supposed to put on the website that they got this banknote with a given number and they were in a given position. Of course, since money do not travel alone, I mean, it's people that discover money. They were in this way, I mean, basically tracking the flow of money along in the United States, but indirectly also tracking the movement of people, the typical pattern that people use when traveling. What they found it was still a power law. Yeah, you see, of course, here the physical limitation is the distance in the United States. And with exponent equal, in this case, around 1.5, 1.6. Of course, it's important to stress that in this case, as in the case also previously of the animals, I mean, we are just collecting so many people together and do this such kind of statistics. We are not doing a statistic for a single person. And similarly, I mean, but this was a more direct way of tracking people. There is this other work by Barabasi, the group of Barabasi, Marta Gonzalez, Cesar Hidalgo, and Laszlo Barabasi, published in 2008, in which they track people using mobile phones. Of course, in this case, you can really track a single person, because each one of us carries his own mobile phone. And you can say, okay, with my mobile phone, I'm now attached to a given antenna in the space, so a given cell. You can say, okay, this person is this time inside the cell. Of course, you cannot track person inside the cell, but you can track movement between different cells. In this case, still they claim that it was a power law behavior with an exponential cutoff, but it's, as you can see, I mean, I'm not really convinced about this power law behavior in this case. It's never straight, as you can see. So you can, basically, you see immediately the exponential cutoff seems to be more exponential. So at the end of this paper, I mean, everybody was very, very happy. I mean, we have like a coherent picture for describing the movement of both animals and humans. They move in the same way, and everything is very fine. But there are basically, in my opinion, two main problems. One is related to the fact that, really, in the case of animals, they are tracking their movements because they move in the space because they are searching for food. So it's a search process in this space. In the case of humans, they are not searching. I mean, they are just doing the daily routine. They go to work, they go to school. From time to time, someone travels and goes from one side to the other side of the United States and so on. The other kind of limitation, of course, it's a methodological limitation because, as I said before, I mean, you are tracking the whole population. So you are putting together all the data of the whole population. But in principle, I mean, you can say that the whole population, for all the population, you have a power law. But then maybe this could be just given by the fact that it's the superposition of different people that maybe just move as a standard run of work, so without a power law. So you have a different kind of distances. The rigidity in the average distances that they cover, when you put everybody together, you have the power law. So I will try today to answer to this, to connect these two things. I mean, basically, really look to individuals and look to individuals, humans, that are doing a search process. And this comes from data that are apparently completely unrelated. So are games that are organized online, and they're called lowest unique bid auctions. These are just two examples. So on this website you have wonderful prizes, so they are very, very attractive. You can win like a supercar, a huge house, and so on. The main point is that, I mean, you have, as you can see, this is a retail price in Australian dollars, so it's a very huge price. So the main thing is that you can bid on a one-dimensional space that is divided in 1 cent, 2 cents, 3 cents, on different value. You don't know what the others are bidding, so on which value the others are bidding. And each time that you bid, you have to pay a fee. Like in this case, the fee is $24. So the main point is that, I mean, there are different rules. There are cases in which the auction expires after a given time, other cases in which there is a minimum number of bids that should be placed in the auction in order to close the auction. But the main point is that, I mean, the situation is so at the end, the winner is the one that made the lowest and unmatched bid. Like in this case, you have like 3 guys bid on 1 cent, 2 guys on 2 cents, 1 guy on 3 cents, 2 guys on 4 cents, and 1 bid on 5 cents. This bid would be the winner in this regular situation because it's the lowest and unmatched bid. This is also unmatched, but it's higher than 3. So specifically, you have really one-dimensional space in which you can bid over a bounded range. The main feature of these auctions are the fact that the value, this capital view of the good that is up for auction is huge. It's at least $1,000. The space, so the value on which you can bid is lower typically of this value, of course, is much lower. And the cost of the bid is like $1, $10. So the main point is that at the end, the winning bid will be a value that is much, much lower than the real price of the good that is up for auction. So you can buy like a supercar for $1,000. But of course, you have to spend a lot of money for bidding because you have to pay each time that you bid. You place a bid, you pay like $10. So basically, since nobody knows what you are doing, all the others, this is just an independent search for this single bid on this one-dimensional space. And so we collected data from different auctions sites. Like in this case, there was this Vespa up for auction. The nice thing is that you can really track the exploration of single individuals in single auction because you have the timestamp, the unique ID of the member, so the user, and the value on which they bid. This is like for cents, 10 cents, and so on. So you can. So the nice thing that appears when you analyze this data is this stuff. So if you track, basically, I mean, this is like bid value as a function of time. Of course, you have to order bids according to the timestamp. Then what you can do is just measure the distance between 2 consecutive bid values, so the bid change. Of course, you have to do like absolute value, so it's just the change.
But excuse me, there were only 2 people bidding in the previous years?
No.
The idea of the... What was the first numerator?
Yeah, no, because I just cut the table. It was much longer. Yeah, but yes. First of
So
all,
one person put so many,
yes.
and they bid 4 cents for a biscuit. That's the idea.
Yes. But each time that they bid, they pay like $1, $2, so I cannot remember how much it was in this case. Now, in this particular example, there is a long list of bids made by the same person. But you see here, this is different, this is different, this is different.
No, but this is not an auction, it's some sort of lottery.
Yeah.
I mean,
I don't understand the auction because from the user 969.86 at 22:53 say 169. 10 minutes later say 31 cents.
So the question is, what is the information the users get from the system? Do they
Well,
know this is the...
The only information is that if they are winning or not at that stage. They don't know anything about the bid value, of course.
But why?
They receive, so this guy received the notice, you are not winning, then he repeats the bid.
But then he was the price. He was the price.
Yeah, because they don't know it wins.
No, I mean, it depends on no, wait a second. Anyway, it depends on the website. Sometimes you have information about...
Mr. Chairman.
Sometimes you have feedback from the website and they tell you, okay, you are winning or not. You know, I mean, since the unique bid can change in long time depending on what the others are bidding. It may happen that you are not winning at a certain point, but with the same bid, you are winning after.
But one thing that they probably don't tell you is that what the others can bid. So
Of course, they will tell you the party that is winning. You know, if you are winning or not.
They bid, and then at the end, all these thousands of people that have bid are paying more than what they like.
No, I mean, there is the limitation that the maximum value on which you can bid is lower than the value of the option.
Yeah, sure.
No, because it's in cent, and I mean, like you can bid at maximum $100. But the price is like, I don't know, $10,000. So the final price is always much lower. The winning bid.
User 6986 at 2204, at the same time he made 3 bids with 3 different values.
Right, because you can bid on more values.
Okay, but 1 minute before he uses another set of values. So what is the rationale for him or her to decide to bid at 0.35, 37, 39, 41, 43, 45, 47, when previously was bidding at 169? So it went down, up.
You just scan. It's
like the more you play, the more you play.
There is no reason.
No, it's just scan the
He saw that he was losing, and okay, let's try.
Go down, but then it starts going up again. You put the money. you put the $10 and put the 31 cents. Okay,
¿Is that legal? Is that legal?
No, for your information, I mean, there are a lot of these websites that are closed by the police.
Actually, 2 years ago it was in the radio station 40 Principales.
Because they are not.
For a reloj hero. You have to call and give the bid. Every time you call, they charge you the call, but there was exactly the same name.
There are still some websites that are live.
I repeat the question because someone disagrees. We don't agree in the answer. So, what information get the users from the system?
You didn't win.
You are not winning. You are winning, or you are not.
No, you are not. You are winning. No.
You are going from the end now.
Finishes.
You are winning at that point. You have the other side.
But this is the trick.
Yeah.
You're winning suddenly.
Yes.
As soon as.
Anyway, what you can do is just forget about this kind of irrational behavior, I would say, and analyze this data coming from this option. I mean, there are people like here making 700 bids in a single option. In this case, there was like a car for option. So basically, you can track the evolution, how they explore this unidimensional space. You see from time to time, generally they move around a given value that they think it's the best or something. And from time to time, they jump. I mean, you can really measure the jumps and make a distribution. But it's quite good, as a power law. You see, in this case, of course, I mean, it goes from 4 order of magnitude. I mean, because you have not physical, real, strictly physical limitation. I mean, you can jump really from 1 cent to 10,000 cents. Of course, you decrease the possibility of winning the game and so on. But it's not really a physical limitation. I mean, it's not like an animal making 1 meter of 10,000 meters. It's a different kind of energy consumption. What you can do is that, I mean, you can track several single users. And the nice thing is that, I mean, the exponent is quite consistent in all cases. So you can do like a distribution of the exponent and see that there is an optimal value around optimal, I mean, it's preferred value around 1.4. And I mean, it's really
So this one of these plots for one single user.
single user, single option. Yes.
One single user is making offers between 1 cent and 10 to the 4 cents.
Yeah.
And once,
I mean, it's a bit change. Yeah.
how many bits is he or she putting? I mean,
In the analysis, I selected only users with at least 150 bits, because otherwise it was impossible to construct a distribution.
I mean, this histogram is usually
What do you mean?
I mean, histogram covering 4 the magnitude with only 100 points.
I mean, I will turn back. I mean,
It should be an error bar.
I will show
It should be
you.
an error bar is vertical size about
No, I will show you
10%.
I will show you later. I mean, I will measure the p-value and to see the consistency between the power of behavior. What you can do. Anyway, so the question is why we have this selected value. Why we have 1.4.
This has to do with the fact that they got the object, this exponent or not?
This is not related.
I mean, this 1.4 does not mean that the ones that follow that slope got the price. No.
No, there is not a relation between getting the price or not getting the price. It's just the strategy that we use. Of course, the idea is that they use unconsciously this kind of thing. They are not random number generators. And of course, you can test the same thing putting together more individuals. So you can collect data from different, putting together all the options and all the individuals on different websites. You can think, okay, there is a clear anisotropy. So the system basically tend to build on low values, right? So maybe there is a difference between changing towards low values or higher values, but effectively, if you separate the two contributions, negative from positive, there is no difference. You can think maybe it depends on the activity of players. So players that bid a lot times behave differently from players that bid only a few times. But there is not significant difference, I mean, more or less, this point is the same. And maybe you can think also, I mean, maybe they change strategy during the game. So at the beginning they behave in a way, at the end they behave in a different way. But still, I mean, if you look to the first bid or a bid lower than, I mean, or the line, there is not really difference. So the main point is really is why they do such kind of things. So we started to model the game. So it's a very straightforward model. I mean, you have this lattice. You can think, I mean, you have to give an initial condition. So you can think, okay, let's start from 0. In the sense that because the tendency is to bid on low values. So at the beginning I see this bit space from 0. Then you can say, okay, this is the case in which everybody bids only one time. I will extend that to the case in which people can bid more times and so on. So at the beginning, I mean, if there is an agent with a strategy gamma, so this would be the probability of bidding on value I. So it just, we assume that it's power distributed. Of course, what you can do is, in principle, you can say, okay, we can study what is the configuration that they obtain in this case. If you have n players, each of them bidding with strategy gamma. This will be given by this multinomial distribution for any given configuration. But the main point is that you have to focus just on the when is unique, this thing. So basically it's just when only a single player bid on value I, none of the others bid on value I, and this may happen with in n different ways because you have n different players. Now let's focus on another agent, single agent that is building with strategy people. And it's competing against this population of players building with strategy gamma. So in this case, you can calculate, this is an approximation actually, you can calculate the probability that this agent makes the lowest unique bid on value V in this way. Basically, it's just the probability of bidding on V or value V. The probability that no one else bid on V times the probability that there is not a single unique bid on values lower than V. Right? Of course, you can calculate like the probability of winning, that is just the sum over all the possible bid values. And you can calculate also the average value of the winning bid in this way. Of course, this is just the case of a single game, but we are interested in calculating. I mean, this is just a game theory approach to the game. So just imagine that we can repeat a given number of times the same game. This capital G times. Of course, if each game is independent, you can write just the binomial distribution, that is the probability of winning small g auction out of capital G auction. And this given just your probability of winning a single auction, right? By this. Then you can say, okay, what is, if I win G auction, how much I spend winning bids? So you can just calculate the sum restricted to this constraint of this multiplication of this value that given by the expression before. Using such kind of expression, you can say, okay, what is the economic return that they obtain in G games winning small G games? It's given by G times the value of the object that I'm winning, minus the money that I spend, divided, of course, by the total number of games. Of course, this is economic return without considering the cost of the fee. You have to compare this value with the cost of the fee. Then, of course, I mean, you can just go to the limit of G that goes to infinity, to infinite number of games. Everything can be basically just considered as an average. So this is the average number of games that you win. So total number of games times the probability of winning a single game. This is the cost, how much you invest. That is just basically total number of games, probability of winning times the average value of your winning game. Putting everything together in this thing, you can obtain the effective economic return of the agent. That is basically given by the probability of winning the game times the difference between the value of the object minus the average value of your winning bid. Of course, when this value is larger than the fee that you pay, you are putting just a single bid, this is the case of a single bid, you are gaining money from the game. So the game is positive for you. You are winning. Of course, if this is smaller than C, you are just losing money. So it's not convenient at all to participate in the game. You can extend, the model, I will not go too much into detail, but there are a bunch of questions. So the main core of the thing is that you have a matrix of transition matrix. So you jump from position J to position I following a Levy flight, in which basically you have this term. So the difference, absolute value of the difference between the two bit values to the power of some exponent. Of course, you cannot come back to the same position and so on. It's normalized and so on. What to obtain are a similar expression for the unique probability for the site to be unique, a probability for being lowest unique. You obtain the same expression for, of course, you have to put these values inside the formal equation for the economic return, but you can calculate the economic return by solving numerically this equation. So what you obtain at the end is this kind of plots. These are just basically payoff matrices. So here you have the exponent of the player on which I'm focusing, beta. Gamma is the exponent of the strategy used by the rest of the population. As you can see, here there is a saddle point that corresponds to an optimal strategy. So I need to do this game. This means that if the population is building with a strategy equal to this saddle point, of course, you see, it's not convenient to move away from this saddle point because I lose money in this direction. The same is valid also for the population. If you are here, this is building here.
Could you say what are the colors? The numbers?
The colors are just the value of the economic return. So here it's 100 is the contour line. Here is the value 100. Here's 102, 105, and so on. So here you are growing here and growing here. Here you are decreasing here and decreasing here. It's a single point. The difference is just between, this is the case in which everybody makes a single bit. This is the case in which everybody makes just 10 bits. Of course, the value of the saddle point depends on the parameter of the model. It doesn't change so much. But the nice thing is that when you tune the model with a typical parameter taken from the real auction, like you see that basically this is the result. I mean, there is an optimal strategy around 1.3, 1.4. So very close to what observed in real data. And of course, I mean, this is a more technical thing. I mean, one can say, why solving all these, writing this equation that are simulation, solving numerical equations instead of just simulating the process? So you can just make a simulation. This was one comment made by one of the referees of the paper. That's why I put this slide. And so the first thing is that, I mean, of course, the result is not really exactly the same, but the location of the saddle point is the same. These are numerical simulation. This is numerical solution of the equation. You see the profile here is quite different. But the nice thing is that, first of all, you obtain a very, very smooth picture in 30 seconds of my laptop by solving the numerical equation. In this case, we needed like 75 hours on the cluster. So maybe it's just a little difference, but I mean, qualitatively it's the same. The other thing is that, of course, you can use the model to make different kind of fitting. Instead of just making the distribution and say, okay, on the log plot and make a straight fit on a straight line, you can say, okay, now I have the model, my transition matrix. I can write an equation similar, very simple for the likelihood. And I can do another fit. I mean, just, if this is the real-time series, so the user is bidding on B1, B2 in order up to BP, assuming that every bit is independent, you can say, okay, the probability of observing this kind of time series given the exponent is just given by the product of the single transition entries. You can tune, of course, the value of alpha that maximizes the likelihood is the best fit in this case. And you can see that, I mean, the plot is quite good, I mean, the kind of fit. Of course, you can use the model, and this makes, of course, sense. In the sense that you can now make a difference. Okay, I have my theoretical model that is this given by the transition matrix sum over all the values. I have my real data. I can generate artificial data of the same length of the real data. I compare the distance that I've observed from the real data and theoretical curve with artificial data and theoretical curve. So I can calculate the p-value. If I'm closer than typically than a random realization, this means that I'm good. Otherwise, not. And in general, what we found, apart some cases, is that the p-value is pretty high. So this means that there is consistency between model and real data. Of course, you can see also that there is some cases there are also big differences between the exponential measure according to the fit on the log plot using the straight line and the one obtained using the maximization of the likelihood function. But in general, there is a good agreement. We also did the scatter plot. In general, you follow the line. But if you plot just alpha as a function of alpha prime, you are consistent. And yes, the other thing is that, I mean, of course, up to now, we model just again using a standard game theoretical model. And this is very strict, so everybody is using the same exponent. I mean, the population is using the same exponent, and the guy that we're observing is using this fixed exponent. Now, of course, there is some noise. I mean, this is not really, it's not reality. And also, this is a strong assumption, of course. So what we made was to relax a bit this kind of assumption. So we make the model, we use an evolutionary version of the model, in which now agents pick at the beginning at random a strategy, that is this exponent of the Levy flight, taken from a generic probability distribution function that we call G0 of alpha. Then they play the game. After that, one agent that is so you see who won the auction at the end. One of the losing agents copied the strategy of the winner plus some noise. And then they play again, and again, and again, and again. So what you observe is that, in this case, for instance, we start from initial distribution was just Filippo. So nobody knew what was the best strategy to do. So what emerged in both cases, both in the case of no mutation or random mutation, is the fact that after a certain number of generation, there is a peak, clear peak. This is the probability. There is a clear peak around the same value of the southern point that we found before. So here we plot the probability that the winning strategy in the game is alpha at this given generation.
But excuse me.
Yes.
In the real game, you don't have any information on the strategy of the other players.
No, that's true. Well, this way you can extract this information by using the time series, but I don't think this is the case.
Well, to copy the strategy in someone, you need to know the
No,
strategy.
I'm not modeling the learning of agents. I'm just trying to relax the condition about the formal model of in which it's a bit unrealistic that everybody uses exactly the same strategy. It's okay. It's just an extension. I mean, basically the result is always the same. So the best strategy is always the same, emerging in both cases. The thing is that, in this kind of model, of course, the final result do not really depend on the initial distribution. If you just plug a different kind of distribution, just a generic alpha to the power of minus lambda, you consider different values of lambda, like 0, in which basically this is a uniform distribution. 2, you have a power of 5, is more or less an exponential distribution. And you monitor along the generation. What is the typical value, the average value of the winning probability of winning, or the winning exponent, or the variance of this distribution? You see that basically it becomes the same. In the case in which you have absence of mutation, so the stationary distribution is just a delta function. So the variance is always decreasing at any finite value of the number of generations. When you have mutation, you reach a steady distribution with a finite width. As you can see here, it's the width is finite. However, this is network perspective. So the main point is that we show, using this kind of theoretical model, that first we show empirically that agents tends to use a typical kind of strategy, this exponent of the verified. Then we prove, using this simplistic version of the game, that actually there was a reason why we use such kind of exponent. And the reason is that this is the optimal exponent in the game, so the one that maximizes the chances to win the game for the various players. But the main thing is that, nevertheless, even if you are very rational, you're using the best strategy when you are playing, the best strategy at the end is not playable because they are lotteries. And this can be seen directly from this plot, because the main point is that the auctioneer organize auction because they gain money. So if you gain money, this means that the value of the object that you are putting up for auction is lower than the total number of bids, the money that you get from the bids. That is this. In the ideal situation in which everybody bids 3 times, you have a population n plus players. And each time that the bid is C, so basically the total gain of the economic return of the auctioneer is just TC times n plus 1. But the economic return, you can prove basically that it's always lower than this quantity. So you are always in the regime in which the game is negative. Of course, why people play? Because playing this game is attractive. Because if you look just at the winners, they typically gain the double of money when they play. So they pay the object that is up for auction, the half value of the price that was like that. So this is just the ratio between the value of the object divided by how much you spend in cost. And that's all. I mean, this is where my collaborators on this project, Professor Luis Amaral and Dr. Andrea Baronchelli from Northeastern University. If you are interested in reading a bit more in detail about that, you can read, especially this paper. And this is just this evolutionary theoretical extension of the model. And that's all.
Okay, so, well, questions, yeah, we start usually by the students, so, because there's someone else got questions.
First two questions. Priority.
Yeah. Do you want? Okay, go ahead.
So, at the time you were asking a power law distribution, did you compare any other distribution with the power law to see what power law is?
Well, we compare with the log normal since the exponent was 1.4, 1.3. But if you do really a statistical test, you cannot find. It's not consistent with the log normal.
But for the optimal strategy, you could compare other strategy.
Yeah, this one, yes.
And if it is much better than you see, then.
In this one, you can, yeah.
You didn't.
No, we didn't try.
Okay.
No, you're right. I mean, in this way, you have many different strategies. So maybe they are not functional at all.
What else? The students?
Or maybe with a different kind of strategy, you can beat the power law, even if there is optimal. If everybody's playing using the power law, and you use a different kind of strategy that is not the power law,
I don't understand very well the motivation. I mean, you're talking about search, but this is here you have no information at all. You're searching.
But when you're searching, you don't have information. Otherwise, you are not searching. What do you mean?
You see what is around you, and there is more probability to find something in some places. Why
this
this game?
is not a random search.
Why this game?
Huh?
Why did you choose this game?
Why did I mean, the main motivation was not related to animals. I mean, we just collected data from this auction because we were interested in analyzing this data. And then we realized that actually they fit with this feature of searching. I mean, you are really searching for a value. You have no information. I mean, in a searching you don't have information, otherwise you don't know. It's like
in the search, the exponent 2 is in the search which is non-replenished search. So you consume the thing and then you should go away because the resource is finished. So it's this kind of search that gives the Levy target exponent.
No, it's the case in which you have scarce resources. It's not.
No, the errors are not replacing. So
not
you know that you have to move.
Otherwise you stay always there. No, of course. No, that's searching.
It's very different from this is very different from this thing, which you don't have information.
Well, in the other one you don't have also a lot of information.
You know that you have to move because there is nothing more here.
Well, where you did no. But here is also
compared to the rest of the space.
But here you also have that information. No? It says that if you read one value and then they say no, you haven't win.
So it's not that.
No, but to have a win is not the same as finding something.
Well, we have to find a value. I mean, it's not like finding a value that is the optimal one, but you don't know which one it is. So
In both cases, you are forced to move.
Yeah,
so that's the point of the scenario.
Now, what is different for sure is the fact that in one case you have the completely isotropy space, so the space is the same, part of this location which you found. In this case, you know it's going to large values when it's not convenient and so on.
Well, I'm a little mystified by your idea of rationality. How do you define being rational?
Irrational is like, I mean, in the case of the game, it's just using the optimal strategy.
But to do that, you
stay on the national.
Yes, but to do that, you need to know the rules of the game.
They know the rules.
No? I mean, I don't understand in which sense anyone doing this thing I mean, to try to optimize something, you need to know what are the rules that might optimize that thing, and then you make a choice. But you don't make a choice.
They are not doing the choices. I mean, they are just doing this in a conscious way.
So they are not.
But by chance, it's very strange that everybody is using the optimal strategy calculating the game. Nevertheless,
but using an optimal strategy is not being rational. Otherwise, animals are also rational because they use an optimal strategy.
Evolution also is a rational trait, not conscious.
That's just that I was mystified about your concept of rationality. For me, rationality means being conscious about being rational.
No, but not necessarily. Because if you lose...
No, I understand your point, yes. It's just about the word.
A robot might be optimizing something. It's not rational.
It is rational, I mean just optimal.
Yeah,
that's not
theoretical.
Why would you expect
If you
that?
want 2 times 2 game, you have to do a choice without knowing what it says.
No, I agree with the point.
Yeah.
Why would you expect that a person playing this game a few times in their life probably will be following a rational strategy? I mean, in the case of the animals, it's quite obvious because the ones that don't do it, the search optimally, they just die, and the ones that are doing that optimally, just they have more chances to survive. But
I don't want to do like a speculation, or because I think it's not what I mean. This could be just related to our notion of the space. It's just the way in which we got used to it.
But as you said, the rational thing is not to play.
No, that's
That's you said it. So.
But then there is the competition, and you want to win. I mean, the rational thing would be that just a single person play the game, you win the auction with,
but then there will be no game.
Exactly.
So I have a question about these changing these bits or the distance between the bits. Because, I mean, if you do the bits in another permutation, you would get a very different distribution of distances, right? So, I mean, but this wouldn't change the bits that you made, and wouldn't change the...
That's why I'm talking about exploration of the states. So you move from one position to another position by making, you are looking for this winning bit. You want that the website tells you, okay, you are winning. So what you do is just, jump in a position, look locally, then jump again.
So if you wouldn't get this feedback, then the distribution wouldn't be like that, or
I don't know.
Because you could just go ahead and place 1,000 bits with a certain distribution, and I mean it depends on the bit distance depends on the order in which you put the bits, but that doesn't change.
No, I agree. It doesn't change the output, the final output. I don't know. It's just a strategy of display.
So I mean, if you would randomize the bits, for instance, would you get a different distribution of?
Sure. First, maybe something that is around the average. Sure. It's just a randomization.
So I mean, if you randomize the order.
Yeah. You're playing something that is,
So it wouldn't be.
No, it would be just something peaked around an average value. Even if the end result is the same.
Maybe it's the same question in another formulation. So there is no memory of each agent bits.
In the
memory in practice.
Now, when you play, you know which value you have been before. In this game, of course, it's a very simplified version, so it's you have no memory. You can go back.
So and then I try to beat high bits and then low ones and totally random.
Yes, I mean, just according to this, these changes obey to this law.
It's not depending on the previous history.
Yes. Well, it depends on the previous history. No, there is no correlation actually. No, just a little correlation. It's really not correlated around what we jumps that obey to law. open distribution.
Okay, more questions? Well, then let's thank Filippo again. We'll be here until tomorrow after lunch, I think, or lunchtime. So you want to talk to him, can be this afternoon or tomorrow morning. He will be in my office, so whenever you want. Thank you. Io recommendo di no.
One, yeah, you have the different agents that are in some sense doing this bits. So they by themselves
Vale, muchas gracias.
I don't know if it's possible to apply. But anyway, I mean, also in the case of the stock market, the other thing is that in general agents are not rational. It's just really a competition.
yeah, in all the games, players can become irrational.
Yeah.
They are under pressure.
In fact, there were some paper about because the difficult thing doing this stuff about game theory as it is economic studies, technology, and always you assume that people is rational. So we make a model in which people is rational. But then the point is that how much this model are effectively valid if people is not rational at all. And there was also a branch of research that we were exploring different classes of games in which people is not rational, not rational, but is irrational. So really, this is really specific.
However, you said that rationality means nothing.
empirical.